Hello, grade 11 class. Today, we are going to be doing a quick demonstration to introduce you to the properties that govern gases. All I've done is I've filled this can here with a little bit of water, put it on the hot plate until the water boiled. I'm going to be submerging this can into this beaker of ice water. That's all. There's no magic afoot. That is all I'm going to be doing. Watch carefully. Notice all of that water coming out. I did not start with nearly that much water. As you can see, the can has completely imploded. Why did that happen? Why is it that when I took a can, an ordinary can, and I submerged it into ice cold water, that it imploded? Why is it that water got sucked up into the can like a straw? Think about that. I'm going to be answering that question by taking you on a journey through our understanding of atmospheric pressure. In particular, we're going to explore the same scientific conundrums that were faced by scientists of the time. Now, this whole discussion of atmospheric pressure started with miners in the 16th century. Now, they noticed that no matter how good they made their water pumps, the water only rose to a level of 32 feet, beyond which no pump could pump the water. So, frustrated that they couldn't devise better pumps, they proposed these questions to famous scientists. In particular, the question was posed to Galileo. Miners asked him, why was it that no matter how good they made their pumps, they could only pump water up to 32 feet? Now, Galileo hypothesized that it's resistance to a vacuum or suction, like a straw, that draws the water up. Now, he came with a major caveat, and then he said, well, it seems nature abhors a vacuum, but only to 32 feet, right? So, not the most elegant of explanations. However, Galileo did document this in one of his famous books, Discorsi. Now, once this book reached Rome, Gasparo Berti had a very famous experiment visualizing the miner's problem. What he ended up doing was took a giant glass cylinder, and this cylinder was over 32 feet long, and he filled it completely to the brim with water, and then inverted it quickly into a tub of water. And what he noticed was that water drained out of the tube, but then it stopped. At what height above the surface of the liquid here do you think that water stopped draining out? Yeah, no, it was 32 feet, right? So from the surface here to here, it was 32 feet. He even added a little bell in there to test whether it was truly nothing above the water. Was it air there, or was it empty space, or was it something else? Unfortunately, due to the poor design of the experiment, you still could hear the bell a little bit, but that begs the question. What is holding up the water? Why is it that the water is held up to this height of 32 feet? And more importantly, what is above that space? This is the thing that really drove scientists. They really wanted to figure out what is above the space of the water. Now, there are some popular explanations. Berti and quite a few others claim that there was nothing above the water. It was just a vacuum. It was a void. There was nothing there. Now, of course, the other side, which is generally when we could not explain something in history, what did we say? It was the spirits. God wills it. So it was the spirits given off by the water that was pushing down the water. Was another very popular explanation. Many people believe that there just could not be nothing. Now, what holds the water up? Berti did eventually agree with Galileo. He said it must be some sort of resistance to a vacuum. There's nothing there, it's a void, and nature has some sort of resistance to this vacuum. Enter Torricelli. Now, Torricelli believed that the water was held up by the weight of the atmosphere. You know, he had this vision that we lived at the bottom of a sea of air, and it was this air that was pushing down on the water. That was what was holding it up to a height of 32 feet. So he designed an experiment to measure the weight of the atmosphere, and instead of using water, he used mercury. Remember, mercury is 14 times more dense than water, so he didn't have to have a 10-meter long tube. He could have a tube that was 14 times smaller. So he only needed a tube that was about 1 meter long, right? Now this, what he developed, was actually the first barometer for measuring atmospheric pressure. So he filled the tube with mercury, just like Berti did with water, to the very brim, and he inverted this tube into a tub of mercury. And what he found was that the mercury did flow out, but only to a height of 760 millimeters above the mercury. Now, from this, he was able to measure the weight of the atmosphere, and he called this atmospheric pressure. Interestingly, this is still a common means of measurement today. If you look at ways we measure atmospheric pressure, one of the ways is in millimeters of mercury. So he also did, variations of this experiment. He didn't do it straight up and down. He moved it around, and he found that more like the mercury level was unchanged as he moved it around. Now the question is, well, what is in the space above the mercury? Is it truly nothing, or is it spirits, or what is it? So he wanted to show that it was in fact empty space, and he did something quite brilliant. He added a little bit of water in the tub above the mercury, and he slowly pulled up the tube. Once the tube got to the water, what do you think happened? What do you think happened? So when the tube got to the level of the water, the mercury rushed out. It rushed out, and the tube filled to the very brim with water. In fact, how long would this tube have to have been in order to see still a little gap at the top? It would have to have been over 32 feet long, right? So this tube was only 1 meter, so clearly the water would shoot up to the top. And he proved that, yeah, there was nothing above the mercury. It was, in fact, a void. Now, Torricelli, again, this was his interpretation, is that, we live submerged at the bottom of an ocean of air, and it's this weight of air that is supporting the mercury in my column. And he actually thought that his experiment failed since the height of mercury fluctuated with changes in the weather. And now we understand that that's not the case, right? Why is it that it fluctuates with changes in weather? Right? There's high pressure systems, low pressure systems. But let's look at this in a different way. Let's look at what scientists often do. Scientists will falsify results, right? They will try to falsify results, right? If it's not peer-reviewed, it is not legitimate. So, Pascal comes along, and he says, no, you're crazy. There is no sea of air, nor the existence of a vacuum. This is crazy talk. I'm going to prove you wrong. I'm going to develop an experiment that will show that it isn't the weight of the atmosphere holding it up. He predicted, okay, well, if we live at the bottom of the sea of air, if I climb a mountain, then we should see that the pressure on my liquid changes, because we're going up, 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 and there's less air now above us. So, Why would there be less pressure on top of a mountain? Well, it's because there's going to be less air. Now, what he did is he got his brother-in-law to climb a mountain for him, and in the process record what happened to the level of mercury as he climbed. Now, what he found was that as he climbed this mountain, the level of mercury dropped and dropped and dropped. So, he proved that Torricelli was right. Right? So he now agreed with Torricelli and said, okay, we do live at the bottom of a sea of air. Right? This was proof. Now we're going to take things in a bit of a different direction here. We're going to look at, well, does atmospheric pressure just push down? Does it push in all directions? Does it push down and up, left and right? Enter Otto von Guericke. Now, he developed air pumps, famously so. And he did this to draw air out of barrels. And he used this to demonstrate the power of our atmosphere. He didn't realize that it was our atmosphere, but what he ended up doing was he actually did an experiment where he took two giant hemispheres, put them together, and there was no glue, there was nothing holding them together, and he pumped the air out of it. Now, as he pumped the air out of it, he hooked up two teams of horses, and he had the horses trying to pull these two spheres apart. This is what it looked like. This is not the greatest photo, but here's the sphere, and there was two full horse teams trying to pull this sphere apart. They could not do it. So, what was holding these spheres together? Why is it that they couldn't pull it apart? Well, von Guericke proposed the weight of the air or the atmospheric pressure pushed the two bowls together. And he calculated the weight of the atmosphere on the two hemispheres was about 1,200 kilograms, and it's not too far off. And von Guericke provided evidence that atmospheric pressure is not just downward, but in all directions. And this is a very important point. Think about it, right? Think about it for a moment. If it was just downwards, right, would the sphere be held together? No, right? The sphere would buckle at the bottom and open up, but it didn't. So it must have been experiencing equal pressure on all sides. It was experiencing the weight of the atmosphere on all sides. Now, Boyle, he heard of von Guericke's experiment, and he wanted to settle the dispute once and for all, because there's still naysayers out there. So what he did is he developed a very good vacuum pump, one that could remove a lot of air, and what he ended up doing was placing a mercury barometer, inside of that vessel. Now keep in mind that at the time science was pretty hip and pretty cool. Again, this is not the greatest picture, but you can see here, this is Boyle, and he's testing out his vacuum chamber. He actually removed the air here, and there was a bird inside. And you can see the bird just kind of like, start to suffocate and pass out. And then when he relieved the vacuum and pumped air back in, the bird revitalized. Amazed the audience. Now, he designed this pump again so he could test Torricelli's experiment, and he stuck the mercury barometer in there. So, what do you think he saw as he pumped the air out of it? Do you think the level of mercury went down? Do you think it went up? What do you think? By pumping out air, what happened to the pressure on the liquid? Right, the pressure went down. So as he evacuated air from the chamber, the pressure felt on that liquid went down. Thus, the mercury level went down. What would have been the level of mercury if he was able to achieve a perfect vacuum, no air at all? Well, it should have been 0, right? It should have not risen up this tube at all. It should have been exactly 0 because there's no pressure pushing on the liquid holding it up. So Boyle could not get it to 0. He was pretty frustrated with that, but he realized even back then that there's probably some sort of error in his apparatus. He recognized there was a source of error. He blamed it on leaks within the system. We now know that obviously achieving a vacuum is insanely challenging, and he didn't get anywhere close to a perfect vacuum, but he did again reinforce Torricelli's hypothesis. So then the question is, well, what is pressure? Pressure is simply the unit of force per unit of volume. So, for example, let's say you're outside in winter, right? You're walking on the snow. What would be better, snowshoes or, say, high heels? Which one's going to sink into the snow? Well, obviously the high heels are. We all know that, but why? Why is that? Well, if you look at the high heels, right, there isn't a lot of area and your weight hasn't changed. So per unit of volume, per unit of area, there's going to be way more force exerted. That's a higher pressure on the ground. But what do we mean when we talk about gas pressure? What do we mean when we talk about gas pressure? Well, we're going to look at a simulation in a second here. But when we analyze the pressure of our atmosphere and the pressure experienced on our bodies, the pressure of the atmosphere is quite large. It's the equivalent of effectively a Volkswagen Beetle on your back. And we've evolved under those conditions, so we're adapted to that. We don't even notice it. But what you do notice is when you start to go underwater. Now, if you go 10 meters below the surface of the water, you're going to experience an additional atmosphere of pressure. You feel that on your eardrums. Another 10 meters down, that's another atmosphere of pressure. And since fresh water isn't as dense as salt water, it's even less than that. So the deeper you go in salt water, you're going to experience more pressure than you would have in fresh water. So let's look at that simulation now, and let's look at actually what happened inside of our can. Okay, so here we have a container, and we're going to pump some gas into it. Okay, so as we pump gas into it, what do you notice happens to the pressure as these gas particles collide with the sides of the container? Well, this pressure gauge shows that the pressure is increasing. The more gas we add, the more collisions with the exterior walls, and therefore the greater pressure. And that's really what pressure is. Gas pressure is going to be the collisions of those particles with the surface of your container here. Now, as I heat this up, what do you think is going to happen? Remember the analogy I used in regards to temperature and how fast particles were moving? I said that a thermometer is a speedometer for particles. Because if you remember, kinetic energy, the average kinetic energy that is equal to the temperature of our substance. So as we increase temperature, we increase average kinetic energy, aka our particles speed up. So you'll notice that as these particles speed up, they make more collisions with the sides of the container. Our pressure here goes up, and eventually our container will fail. Right? This is why you don't throw closed containers of hairspray or propane on a gas, on a campfire, because they will explode. Now, if we cool our particles down, you'll notice the opposite happen. Right? The particles will slow down, and as a result, they'll make less collisions with the side of your container, and the pressure will go down. What do you think will happen if I change the volume of our container? What do you think will happen if I make it smaller, per se? Do you think that there will be more collisions or less collisions with the exterior of our box? Well, the answer is there will be More collisions. Watch what happens to the pressure. Boom, the pressure shoots up. I decrease the size again, the pressure goes up again, right? So by changing the volume, we can also modify how many collisions occur. Okay, so now let's finally explain, well, what the heck happened in that can demonstration. So I had the can on the hot plate, so here's our can here. My amazing drawing skills. Here's a hot plate, and there was an opening in the can, and there was a little bit of water in it, and we heated this water up to a point where it was boiling. So, we had these high energy gas particles coming off our liquid. They were hitting the sides of our container, but they were free to escape. And that's what you saw, right? You saw steam rising from the top. Now, since this container was not sealed, the pressure in it was not going up, right? It could freely escape out the top of our can. So the pressure pushing in on the can, which was 1 atmosphere of pressure, is equal and opposite to the pressure that was pushing on the inside of our can. So our can didn't expand and blow up, it didn't contract and implode. It was just in a nice, happy, steady state, right? Pressure was equal on the inside and outside. But that all changed when I inverted it and put it into our giant beaker of cold water. Now, by putting it in the cold water, what did I do? What did I do? Well, I sealed it off. There is no longer an opening. And since I sealed it off, this gas was now trapped. And it did start out at 1 atmosphere of pressure, right? That's what it was when I inverted it. But quickly that changed. This water was very cold, so what happened to the speed of our gas particles? Well, they slowed down, right? And when they slowed down, they were making less collisions with the exterior of our container here, with these walls of our container. And as a result, the pressure on the inside, it went down, right? I'm showing the magnitude of pressure here just by the size of the arrows. So the pressure experienced on the inside of our can went down. And what further decreased the pressure? Well, what happens when you cool steam down? Well, it condenses, right? It condenses into a liquid. Now, we were removing gas particles further from the air inside of our can, right? We were turning it into a liquid by cooling it down. So that further decreased the pressure experienced on the inside of our can. And what did not change was atmospheric pressure. So the pressure experienced on all sides of our container, because remember we established that atmospheric pressure acts in all directions, that did not change. And as a result, our can literally got crushed by the atmosphere. Now onto that second question. Why is it that we sucked water up into the can? Why was it that, when I pulled that can out, there was a lot of water trapped inside of it, right? Why did that happen? Well, this is the same reason that you are able to drink from a straw, right? Inside of our can, we established there was extremely low pressure. And we've established through understanding the history of atmospheric pressure that what held up the water in that column, well, that was atmospheric pressure. So we still have atmospheric pressure pushing down on that liquid. And pressure always goes from high to low. So that pressure pushing down on the liquid pushed the water up into the can because there was low pressure pushing down on that water inside of your can. And that is why the can imploded and why it sucked up water. Right on.